We're going to walk through an example where we're going to use the logistic equation to model population growth. We are told that a state park introduces a population of 100 deer into a protected habitat. Biologists estimate that the environment can support a maximum of 1,000 deer, which represents the park's carrying capacity. The intrinsic growth rate of the deer population is estimated to be 0.6 per year. We're going to model the deer population over time using the logistic growth equation. Let's start by writing down that equation. That equation is dp dt, where p is our population, is equal to r times p. R is our intrinsic growth rate. And we're going to multiply this by 1 minus p divided by k, where k is the carrying capacity. Let's write down that our initial population, p at time 0, is 100 deer. And our intrinsic growth rate is 0.6 per year. And then our carrying capacity, k, is equal to 1,000 deer. Let's go ahead and put all of this into our model. We have dp dt is equal to r, which is now 0.6, times p, times 1 minus p over k, which is 1,000. This equation is a separable first-order ODE. We're going to use separation of variables to solve this equation. So let's start by putting the p's on the left and the t's on the right. This gives us dp all divided by p times 1 minus p over 1,000 is equal to 0.6 times dt. To make things easier on the left-hand side, let's multiply the top by 1,000 and the bottom by 1,000. That will get rid of our fraction. This gives us 1,000 dp all divided by p times 1,000 minus p. And that's a lot easier to work with. And then our right-hand side stays the same. We can solve this by integrating both sides. Let's now split up our left-hand side using partial fractions. Let's write 1,000 all divided by p times 1,000 minus p and see what that equals. We can write this as a divided by p plus b all divided by 1,000 minus p. Let's cross multiply on our right-hand side, and we get 1,000 a minus a times p plus b times p, and that's all divided by p times 1,000 minus p. We can now set 1,000 on our left equal to this expression on our right. Let's write that down. We have 1,000 is equal to 1,000 times a, and then let's factor out a p, and we get b minus a. Just to make this easier, I am going to rewrite the left-hand side like this. I'm going to write it as 0 times p plus 1,000, and then the right-hand side is going to stay the same. We can now see that 0 is going to equal b minus a, and then 1,000 is going to equal 1,000a. This first equation tells us that b is equal to a, and then our second equation tells us that a is equal to 1, and we can plug that back up into our first equation, and this tells us that b is also equal to 1. Now we can rewrite this integral into these two pieces. Our first piece is a divided by p, so that is 1 over p. And then our second piece is b, which is 1, all divided by 1,000 minus p. And then we have our right-hand side, the integral of 0.6 dt. Now we can go ahead and integrate. On the left, we have natural log absolute value p. Notice that we have a minus p there. Because of that, we need to multiply our answer by a negative. So this is minus natural log absolute value 1,000 minus p. And then on our right-hand side, we have 0.6t, and we're going to add on our arbitrary constant that I'm going to call C1. Let's now combine our left-hand side. I'll remind you that natural log A minus natural log B is just natural log of A divided by B. Let's use that. So on the left, we now have natural log absolute value of P all divided by 1,000 minus p. And then our right-hand side stays the same. We are running out of space, so I am going to grab this and take this to the next page. To get rid of the natural log, we are going to exponentiate both sides of the equation. So on the left, we just get e to the ln, and those cancel out. So our left-hand side is just the absolute value p divided by 1,000 minus p. And then on the right, we have e to the 0.6t plus c1. If we have e to the a plus b, we can rewrite this as e to the a times e to the b. And I'm going to do that because it's going to make it easier. I'm going to write our right-hand side as e to the c1 times e to the 0.6t. And then our left-hand side is going to stay the same. Now we need to get rid of the absolute value. So we're going to introduce a plus or minus, and I'm going to pull that to the right-hand side. On the left, then, we just have p all divided by 1,000 minus p. And then on the right, there's our plus minus e to the c1 times e to the 0.6t. Let's make this easier, and let's assign plus or minus e to the c1 to just be c. So we can rewrite our right-hand side as c times e to the 0.6t. We need to solve for p, but before we do that, let's go ahead and let's find what our constant c is equal to. We were told that our initial population, p at 0, was 100 deer. So let's let t be equal to 0 and p be equal to 100, and we're going to find c. This gives us on the left, we have 100 all divided by 1,000 minus 100. And then on the right, we have c times e to the 0.6 times 0. E to the 0 is just 1, so this tells us that c is equal to 100 over 900, which is just 1 over 9. Let's now rewrite our equation, and we have p all divided by 1,000 minus p is equal to 1 over 9 times e to the 0.6t. This gives us p is equal to 1,000 minus p times 1 over 9 times e to the 0.6t. There's a lot of algebra here. Let's get rid of this fraction, and let's go ahead and multiply both sides of our equation by 9. This gives us 9p is equal to 1,000 minus p times e to the 0.6t. Now we're going to multiply through on our right side. This gives us 1,000 times e to the 0.6t minus p times e to the 0.6t. Hang with me, we're almost done. Let's pull the p on the right to the left. So we have 9p plus p times e to the 0.6t is equal to 1,000 e to the 0.6t. Let's factor out a p, and we're left with 9 plus e to the 0.6t, and then on the right, everything stays the same. Now we can go ahead and solve for p. P is going to be equal to 1,000 e to the 0.6t all divided by 9 plus e to the 0.6t. Notice that we have an exponent on both the top and the bottom. Our solution is going to be a lot easier to work with if we only have one exponential. So what we're going to do is we're going to multiply both the top and the bottom by e to the minus 0.6t. Now our solution is p of t is equal to 1,000. I'm going to switch the order of these two terms. So we have a 1 first, and then we have a 9 e to the minus 0.6t. Since our population is deer, let's go ahead and include units in here. So we're going to put deer, and then that's our final solution. If we want to find out what the population approaches as time goes to infinity, we're going to take the limit as t goes to infinity of p of t. This term is going to equal e to the minus infinity, which is 0. So we're just going to be left with 1,000 over 1, which is 1,000 deer. And that's exactly the park's carrying capacity. So we know that we've done the problem right. And that's it. You now know how to use the logistic equation to model population growth and interpret the long-term behavior of the population. You should now be all set to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.